Okay, so suppose we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder available in the kitchen. How many pancakes can we make? Anybody have a real fast answer? I've done this slide a million times and I don't remember the answer, so I'm not fast either. Well, how would we figure this out? Well, from 3 cups of flour, how many pancakes could we make? 15. So what we're doing there is we've got 3 cups of flour times, we make 5 pancakes, I'm going to call them PC, per 1 cup of flour. And so we could make 15 pancakes from 10 eggs. Well, we can get 5 pancakes for every 2 eggs, right? So that's going to be what, 25 pancakes? 10 times 5 divided by 2. And then 4 teaspoons of baking powder. It takes 0.5 teaspoons to make 5 pancakes. So that one we might want to use a calculator for. 4 times 5 divided by 0.5. Yeah, I did something wrong. Syntax error. Oh yeah. Try that again. 4 times 5 divided by 0.5. 40. So how many pancakes can we make? 15. Why only 15? Because we're going to run out of stuff, right? When you run out of an ingredient, then you can't make any more. We can't make 15 plus 25 plus 40 pancakes, right? That'd be silly. Yes?
The eighth one, where did the second PC come from? The first 5 PC over 2 PCs?
Oh, it should be eggs.
Oh.
Thank you. It came from a brain fart. That's where it came from. Thank you. Yeah. So it's 2 eggs. We're making pancakes. We run out of flour after we've made 15 pancakes. We are done. You can't make pancakes without flour. You can't just use eggs and baking soda, baking powder. That's not going to make a pancake. It's going to make something else, but it's not going to make a pancake.
You always pick the lowest number.
Always the lowest. So our strategy here was we look at the different ingredients, we calculate how much product we could make from each. The smallest one is the one that we can make. Okay? Because once we hit 15, we've run out of an ingredient. So of course, well actually, we're not going to chemistry yet. We're going to stick with the pancakes here. So 3 cups of flour. We did the calculations. That could make 15 pancakes. 25 eggs from... This many eggs will give you that many pancakes. So stick with that. This much baking powder will give you this many pancakes. So this is the thing that's limiting. This is the ingredient that limits how much pancakes we can make. And this is our theoretical yield. So if we did everything just right, we'd end up with 15 pancakes. Now, I don't know about you, but when I cook pancakes, it often comes out a different number. Because I make them too big or too small, or you drop one on the floor, or you get distracted and you burn a couple, right? Stuff happens. But if you did things just according to the recipe, this is what you get, okay? So we're cooking the pancakes, we burn 3 of them, and 1 falls on the floor. It's a bad day for pancakes. We had enough flour to make 15 pancakes, but we actually only produced 11 pancakes. Our theoretical yield In theory, we could make 15 pancakes, but we're a klutz today, so we only made 11. 11 pancakes is how much we actually made. That's called the actual yield. How much you could make if everything goes perfectly is the theoretical yield. As in real life, in chemistry, things usually do not go perfectly. It's very unusual to get your theoretical yield. We use percent yield to compare our actual yield with our theoretical yield and kind of give an idea of how well this went. So percent yield, percent is the part divided by the whole. Here's the part. Let's see, do I have that written out? I maybe don't. I'll write it out here. Percent yield equals the actual yield divided by the theoretical yield times 100. It's the part divided by the whole. How many you actually made divided by how many you should have been able to make. Multiply by 100, we get 73%. So we had a 73% success rate. Not horrible, but not great either. Right? If you were making pancakes for a living in a restaurant, they might fire you. I don't know. If you kept up doing that. Any questions? The actual yield has to be determined by either doing the experiment or by having someone tell you what it is. Okay? So in problems on an exam, we're going to tell you what the percent yield is. No, I'm going to tell you what the actual yield is, and you have to calculate the percent yield. The actual yield is almost always less than 100%. Because some of the product doesn't form, or some of the product is lost in the process of recovering it. I know that happened to one group when they were burning their magnesium. The crucible fell, and some of the product fell out. They scooped up what they could, but they lost some. It happens, right? So the percent yield is lower than the theoretical yield. There are occasions when your percent yield is higher than 100%. Is that possible? Well, if I have, if I'm making pancakes, and the pancakes have to be a certain size, is it possible to make more pancakes than the recipe calls for if I'm not making them smaller? Making the pancake thing, it's not my favorite analogy, but it's the one in the book. What if we're making sandwiches? And we had 4 pieces of bread. We could make 2 sandwiches, right? Could we possibly make 6 sandwiches with 4 pieces of bread? Not if your sandwich has 2 pieces of bread, right? You can't make more. So how could an actual yield of a chemical be larger than the theoretical yield? It usually indicates that some mistake was made. And it's not a mistake in how the product forms. It's not that you screwed up and you made sandwiches with 1 piece of bread instead of 2. Something happened, like there's a contaminant in your product. When I was in college, we were doing an experiment, and we were burning things in a crucible, and a housefly flew over their crucible. The heat killed it. It fell into the crucible and burned up. What? I mean, crazy things happen. Right? So that messes up the mass of your product, right? Because you've got a burned up housefly in there. That's going to add mass. That could give you a percent yield that's higher than 100%. Did you actually make more than is possible? No, you've just got a burned up housefly in there. So I admire this guy. He went around the building and caught 10 flies and burned them up in crucibles and measured the average mass of a housefly and subtracted that off from his data. I can't remember how it turned out, but I just love that story. So that could happen. Sometimes you're collecting something, a precipitate, by filtering it, and it's wet, right? And if you don't let it dry completely, it's still damp, and so you're getting the mass of the water along with the mass of your product, and that makes the mass look higher. It actually isn't. So a percent yield higher than 100% happens, but it means that something went wrong. Okay? Okay, so here's a summary of these different terms. The limiting reactant is the reactant that gets completely used up. This is what limits how much you can make. It's the reactant that will give you the smallest amount of product. The theoretical yield is how much product can you make based on the amount of the limiting reactant. This is, everything's perfect. The actual yield is how much you actually make. And the percent yield is the actual yield divided by the theoretical yield times 100. If you did it perfectly, and the actual yield was the same as the theoretical yield, you'd end up with 100%. It doesn't happen, but it's a nice thing to shoot for. Any questions? So we're going to start doing this with chemistry by looking at just moles. We're going to leave the grams out of it for now. So here's an equation. Titanium reacting with chlorine to form titanium 4 chloride. What are the limiting reactant and the theoretical yield if you start with 1.8 moles of titanium and 3.2 moles of chlorine? So what we're going to do here, the approach is we're going to use stoichiometry to find out the amount of product that we can make from each reactant, just like we did with the pancakes and the ingredients. We're going to say, well, if we have 1.8 moles of titanium, how many moles of product could I make? 3.2 moles of chlorine, if that all gets used up, how much of this can I make? The limiting reactant is the one that gives the smaller yield. The theoretical yield is the smaller yield. So am I supposed to do? Okay, I wasn't supposed to do it on this page. I'm going to do it on this page. Same equation, same question, more room to write. So I have 1.8 moles of this, and I have 3.2 moles of this. And I want to know how many moles of product can I make. Now, what's different about this than the previous problems we've been doing? How many numbers are there? There's 2 numbers. I have an amount for both reactants. That's the big clue that this is a limiting reactant problem. I've got 2 amounts. I need to do 2 calculations. They're very similar. So I want to take moles of titanium and find moles of titanium chloride. So moles of titanium, and I want to find out moles of titanium chloride, TiCl4. So this is a one-step thing. 1.8 moles of Ti. I'm going to multiply. My fraction is going to be moles of titanium 4 chloride, and I want to divide by moles of titanium. We're not doing grams to moles to moles to grams. We're just doing the middle part. This is easier. Sometimes students say, well, that couldn't be easy. I'm going to make it more difficult. I'm going to do moles to grams to moles. You can't do that. That is always, always wrong. Okay? It's grams to moles to grams, or you can cut some pieces off, but you cannot rearrange things. So what we're doing here is the middle. So grams to moles to grams is our stoichiometry mantra, right? But here we're just doing the middle part. We're leaving the ends off. Oh well. I want to get rid of that mess I made down here, but whatever. Okay. Mole ratio comes from the balanced chemical equation. 1 mole of titanium will make 1 mole of titanium chloride. You may be thinking, why do I have to write this out? Well, because when it gets more complicated, you need to be able to do it. So if I used up all the titanium, I could make 1.8 moles of product. Now I'm going to take the other reactant. I'm going to go moles of chlorine to moles of titanium chloride. I could calculate other things. I could start here and I could calculate the moles of titanium, but that's not what I want. I want to go to the same thing. I want the product, just like when we were doing pancakes, you know, with the baking powder and the eggs and the flour, we're calculating the same, we want number of pancakes for all of them. So we've got 3.2 moles of Cl2. I want to multiply by moles of TiCl4 and divide by moles of Cl2. Well, there's a 2 in front of Cl2, so I'm going to write that down here. There's an understood 1 up here, so I'm going to write that down. Do the math, I get 1.6 moles of TiCl4. How many moles of TiCl4 can I make? 1.6. It's the smaller one. Because once I've made 1.6, I have used up this ingredient, this reactant. I don't have anything more. I can't make any more. Yeah, there's some titanium left, but it's just going to sit there because it has nothing to react with. So we choose the smaller one. This equals the theoretical yield. That's everything going perfectly. This is the most we could make. So that's the theoretical yield. What is the limiting reactant? The limiting reactant is the one that gave you the theoretical yield. It's the one that gives you the smaller amount of product. It's the one that's going to run out. It's the one that limits how much you can make. Yes?
Does the 2 moles, the 2 in front of the mole come from the 2 after the Cl?
The 2 here in front of moles of Cl2 comes from the coefficient in the chemical equation. Because this is telling me that 2 molecules of this would make 1 formula unit of that, or 2 moles of this will make 1 mole of that. Any other questions? Let's do another one. Consider this reaction. If you begin with 4.8 moles of sodium and 2.6 moles of fluorine, what is the limiting reactant and theoretical yield of sodium fluoride in moles? So I've got my balanced chemical equation, and I'm going to write my numbers. Under it, it says 4.8 moles of sodium. So I'm going to write 4.8 moles under sodium. And 2.6 moles of fluorine. It wants the limiting reactant and the theoretical yield of sodium fluoride. So, question mark, this is what I'm trying to find, and it says in moles, so the unit there is going to be mole. I have quantities for 2 reactants. So I'm going to have to do 2 calculations. Remind me to oil that door. So it's just like... It's ripping at my soul. Just, yeah. So, two calculations. So we want to go from moles of sodium to moles of sodium fluoride, and we want to go separately from moles of fluorine to moles of sodium fluoride. So moles of sodium to moles of sodium fluoride. So 4.8 moles of sodium, and I want to multiply by moles of sodium fluoride and divide by moles of sodium, because I want those units to cancel out. This is dimensional analysis with weird things, moles of stuff, right? Look at the chemical formula to find the numbers for the mole ratio. 2 moles of sodium make 2 moles of sodium fluoride. So the math on that one is really simple, 4.8 moles of sodium fluoride. And then I'm going to do it again with the fluorine. So moles of F2, stupid door, to moles of sodium fluoride. 2.6 moles of fluorine. I've got one arrow, moles of sodium fluoride on top, moles of fluorine on the bottom. Once you see the pattern, it's very straightforward. Until you see the pattern, it's really confusing. In front of F2 is an understood 1, and in front of this is a 2. So I'm going to write 1 in front of moles of fluorine and 2 in front of moles of sodium fluoride. So I'm not going to tempt fate. It's not a good day for me to tempt fate. I'm going to do that on my calculator. Oh, I was right. 5.2. So I've got 2.6 times 2 is going to give me 5.2 moles of sodium fluoride. So I have two amounts here. The smaller one is always the answer. So 4.8 is smaller. This is how much you can make. That's the theoretical yield. I'm just going to call it TY, theoretical yield. If you do a problem like this on, I won't see it on an exam, but on a lab, and you don't pick one of these, it's going to be wrong. Because you've got two answers here, you need to tell me which one is the answer. It's the smaller one. Yes?
As far as the limiting reactant, is that the 4.8 mole or the limiting reactant is just sodium?
The limiting reactant is just the chemical. It's just the formula. So this is the amount we can make, the theoretical yield. The limiting reactant is going back here, it's this guy. So once you've identified the smaller, just go back to what started that calculation, it's sodium. Sodium is the limiting reactant. Na is the limiting reactant. And, you know, if you do little abbreviations like that on your post-lab question or something, I'm fine with that. But if you just show the calculation and don't choose anything, then you're going to lose points. Any questions? Oops, didn't mean to do that.